My name is Nasir Ali. I am a specialist tutoring at the Learning Common, and today I will do the test review for the Chemistry 1045, or we call it like General Chemistry 1. And the metric conversion, if you see all this, the unit and all this, the unit is like 10 power some number. And let's start for the first example. And how many nanogram are in the 65.5 milligram? And like our idea to convert like milligram to the nanogram. And the first of all, we have to change the milligram to the gram. And after that, the 65.5 milligram converted to the milligram to the gram, like 1 gram equal 1,000 milligram, and we got this the result 0.0655 gram, and then I have to convert the gram to the nanogram, and this the number like 0.0655 gram multiplied by 1 nanogram equal 10 minus 9 gram, and I got the final result like 6.55 multiplied 10 power 7 nanogram. And the other example, how many cubic inch are in the 4.5 meter cubic, and like our journey, I have to convert the meter to the cubic to the inch, and then I uh, multiply by the cubic to get like a cubic inch. Let's start and to figure out how can to solve this problem. Like 1 inch equal like 2.54 centimeter, and then I have to convert like the 1 meter to the 1 meter to the centimeter. Like here, then 1 meter equal like 1 inch equal like 2.54 centimeter, and then 1 centimeter, sorry, 1 meter equal 100 centimeter, and I convert like the 1 meter equal 39.37 inch, but we keep in our mind and we want to convert it to the cubic inch, and the number of them is giving in the question 4.5 meter cubic. I multiply by this number, but we keep in our mind and we have to convert to the cubic inch, and we raise it to power 3, and after that we got like inch in the cubic. If you see this the number 4.5 multiply by the result when you get here 39.37 rising to the power 3, and like our final result 2.7 multiplied 10 power 5 inch cubic. And the other example, and what is the mass of 2.5 liter of the mercury, and they give me the density. If you see the density, this is the number 13.546 gram over centimeter cubic, but for the density like D equal the mass over the volume. If you see the unit of the density, the gram over centimeter cubic, and therefore, and I want to match the unit with the volume after after I find the mass of the mercury. Here I have to convert the 2.5 liter to the centimeter cubic, and the idea to cancel the unit and end up just with the gram. Let's start to figure out how can to cancel this the unit out, and like here like 1 centimeter cubic equal 1 milliliter. Therefore I have to convert the 2.5 liter to the milliliter, and one letter equal 1,000 milliliter. I cancel the letter here, I cancel the letter here, and just I keep milliliter. I convert the 2.5 letter to the uh, uh, 2,500 milliliter, and then I do multiply by multiply the volume, multiply by the density, and the density is and after we match this the unit and we cancel the unit, like milliliter go to this milliliter and we stay and just the gram, and our result 3.4 multiply 10 power 4 gram of the mass of the mercury. I mean, the key point for this equation, we have to watch the unit and we have to match the unit, and the key answer here, like 1 centimeter cubic equal 1 milliliter, and this is the key point for this example. Hi, for the isotope, this is the isotope, and each element it has the isotope, maybe one or two or three, and dependent on the element in the periodic table. For example, the sodium isotope, it has like 4 isotopes. One of them is the 23 like sodium become like this, the isotope. What's that mean, the isotope? The number of the neutron is different than the original element of the sodium, which is the atomic mass, or the mass number of the original sodium is 20, but in this one is 23 atomic number. And also the sodium, it has the 4 isotope, and for like one of them is 24, 22, and as I mentioned, the original close to like 20 and 23. And be careful for the isotope. The isotope for just the different by the number of the neutron. And how can I know the mass number? The mass number of this, like for any element, for example, for the sodium here, 23, the total number, what does that mean? The number of the proton plus the number of the neutron. And the atomic mass, which is like representative by the Z letter, and the number of the proton and nuclear charge. What means nuclear charge is but the positive charge, because the neutron is most of the time no charge, zero charge, and the proton is the positive charge. This we call like nuclear charge, which the proton is the positive, and they make the nuclear is positive. Most of the time, it attract the electron. For this example, determine the number of the proton, neutron, and the electron for the following element. If you see like palladium, the palladium, it has the mass number 206. This 206, the proton plus the neutron. And the bottom number 82 is the number of the electron. If I want to figure out the number of the electron is 82, and the 82 is equal the number of the proton is 82 also. But if I want to figure out the number of the neutron, how can I figure out this number minus this one, and they give me like 124, the number of the neutron. The other one is the 10, and the 10, if you see the oxidation number is positive, that means the number of the electron is less. How? Because the 10 is lost 4 electron from their orbital. Therefore, if I want to figure out the number of the electron is like 50 minus 4 is 46. And the number of the electron, number of the proton is 50. If I want to figure out the number of the neutron, 118 minus 50, I got 68. And the same thing for the selenium. If you see the oxidation number, which is like gain 2 more electron. If I want to figure out number of the electron, 34 plus what he gained, the 2 electrons to their orbital, plus 2, and I got the 36. Number of the proton is 34. If I want to figure out the number of the neutron, the total mass minus the 34, I got 45. And for the other example, for the the fraction abundance, and this is the topic we have to know, like the abundance of the like element in the environment. And if you read this the example, determine the atomic mass and identify an element have the following isotope and natural abundance. Like the natural abundance, which is like 19, with this the natural atomic mass unit with the 90% and 20%, and this the atomic abundance, sorry, 20 with the 0.26%, and this abundance like 21 with the 9.2%. First of all, we have to follow the law here. If you see this, the sum of the fractional abundance multiplied by the isotope mass. Here I am for the how can to solve this example, and I have to multiply the mass multiplied by the fractional abundance isotope. And first of all, I have to convert the percentage to the decimal, and after when I convert this with the decimal number, I have to multiply abundance with the decimal number, and then I add all of them together to get the final answer for this, the average atomic mass abundance for this example. And after when I add the first multiply abundance for the with the after when I converted to the decimal, and I add them together, I got the result 20.118 atomic mass to solve this problem. Nomenclature. This is the topic, and they teach us. Sorry, they teach us how can to name the molecule, and how can to name like binary molecule, and we have to know all these like prefix. Prefix like mono is 1, di is 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nano 9, deca is 10. But the first of all, if I want to name the binary molecule, and the first element, which is like most of the time is the positive, I keep it as is. The first element, I mean, what's mean as is like the same name from the periodic table. Like sodium, I keep the sodium the same thing, or nitrogen. Like nitrogen, I pick up this the name from the periodic table, I write it in the first. But the second thing, or the second element, I have to change the suffix to from the periodic table, and the three exactly for the 3 letter to the IDE, and I change this the root. And after that, I name this like my binary molecule for the sodium chloride. If you see sodium, I keep it as is, but the chloride, I change the root from IDE. Let's say here for this, the like carbon dioxide. If you see, I keep the carbon the same from periodic table, but I add here 2, because here we have 2 oxygen. I use like di, but oxygen I change it to the oxide. Like I change the three suffix letter to the IDE. I say like carbon dioxide. If you see this, the other element like nitrogen, uh, nitrogen tetraoxide. If you see here, I do have the two element from the nitrogen, but here I have to add di because they have two element di nitrogen, but I keep the nitrogen as is. But the oxygen, it has the four element of the oxygen. I use tetra oxide, and keep going for the name of this, the binary molecule. For the naming binary ionic compound, the same thing we use, but the different here, like the oxidation number, we have to use the Roman numeral. And if you see this here, lithium as is from the periodic table, and we change it to and lithium, just we change the chlorine to the chloride. Magnesium, here magnesium dichloride. If you see the magnesium, we keep it as is, but here the di, like two chloride. And here for this one, the iron chloride, if you see this, the iron number and the number one Roman numeral, and the chloride. And iron oxide, if you see this, the oxidation of the iron and the oxygen is like 2 iron 2 on, and then oxide, and keep going to name for this binary molecule and the binary ionic compound, and keep all this system in your mind. How can to name, but keep in your mind, in both cases we have to change the suffix from the from the root word to the IDE, and in both cases. How can to name the polyatomic ion? The polyatomic ion, that means like this compound, it has like many atomic, more than three or more than two. But before I go for this naming, and I want to introduce the some like this the compound, and we have to familiar how can to name it. This is the common name for the ammonium, like NH4, and the mercury, and the carbonate. The carbonate, if you see the root here, ATE, that means this compound, it has like more than two oxygen, or more than three oxygen with the carbon, and like abundance of the oxygen close to the center atom of the carbon, and we use ATE. And sulfate, if you see the sulfate, like 4 oxygen, ATE. And but here the sulfite, it has like more, like less than 4 oxygen, and we change it to ITE. And nitrite, if you see 3 oxygen, ATE. And nitrate, if you see like 2 oxygen, and so on, so far for the other carbon. If you just focus about the number of the oxygen, if the number of the oxygen is high, my my root is ATE. If the number of the oxygen is less, I change it to ITE. And we use the same process, or the same step for naming the binary molecule, to change the root of the second element to the IDE. Like for example, here, if you see the calcium, we keep the calcium, the same thing. But here, carbonate, if you see this, the carbonate, it has like more oxygen, and the lithium sulfate, it has like more oxygen, and the iron 3, or this is the oxidation number, and phosphate, it has more oxygen attached with the phosphoric group, and so on. For the empirical formula, for this the chemistry, or for this the topic, I have to know the empirical formula if they give me some percentage or the gram or for the compound. For this example, if you see the aspirin has mass percentage composition 60 carbon, 4 hydrogen, 35 oxygen, and after that he tell me determine the empirical formula for the aspirin. Here, the first of all, I have to like convert the percentage to the gram, because here, like when he give me like 60% of the carbon, I assume from the total mass of this the aspirin is 100, and then I have to convert the gram to the mole. After when I convert it to the mole, I compare my mole for the carbon, hydrogen, and the oxygen, which is the less number of the mole. I divided all these three elements by the less number. It's not by the large number. I am looking for the less number, and then if I find like some like decimal number, I have to convert the decimal number to the whole, or to the whole number. And the whole, what's mean and the whole number? I have to convert it to the even or the odd number to make it like the whole number. I cannot use decimal number in the empirical formula. For this example, as I mentioned, like 60% or 60 gram from the carbon, I go to the periodic table, I see the atomic mass of the carbon is the 12 gram per mole, and then I convert the gram to the mole. If you see 16 multiplied with 1 mole equal to 12 gram, I cancel gram with the gram and just left the mole for the carbon. The same thing for the hydrogen, I end up with the 4.4 mole of the hydrogen, and the same thing for the oxygen, 35 gram, but I go to the periodic table, I see 1 mole equals 16 gram. I cancel the gram with the gram. After when I make the division, I got like 2.2 mole of the oxygen. If you see the oxygen, it has less mole compared to other element. Therefore, I divide by this number for all these three elements. But if I divided oxygen by itself, they give me 1 mole. But if I divide it by the hydrogen, they give me 2. When I divide it by the carbon 5, they give me 2.24. But here, our problem here is the decimal number for the carbon. I want to round up the 2.25 mole of the carbon to the whole number, even though to the even or to the odd number. Here, the only number I multiply this, I multiply this number to make him like even or the odd number is number 4. If I multiply by 3, they not give me the whole number. If I multiply by 2, they not give me the whole number. If I multiply by 1, also they give me the same number. Therefore, I go to the highest number, to the 4. If I multiply 4 with this number, and they give me 9. But after when I got or resolve This is the problem. To convert the decimal number to the whole number, I use the same number here for to multiply hydrogen and oxygen to get my final result. And therefore, if you see, I have 9 carbon, 8 hydrogen, and 4 oxygen. And my empirical formula is supposed to be become like this: carbon 9, hydrogen 8, oxygen 4. Just follow this step, but the important thing, this step, when you got the like decimal number, we have to convert it to the whole number, and the whole number doesn't matter if become even or the odd, but I want like the whole number is not decimal number. This slide they talk about the stereochemistry. If you see for this example, and he asks you about how many gram of this trisodium phosphate can be produced, and we can get it after the reaction is like run out. And when the 5 gram of the sodium dihydrogen phosphate react with the 2.5 sodium hydroxide, and then he gave me the molar mass for all these compounds: the sodium dihydrogen phosphate 120, and sodium hydroxide 40 gram over the mole, and the trisodium phosphate 163.9 gram over the mole. And here they give me the reaction formula, and first of all I have to balance each element before I make my calculation. If you see, the sodium here is like 1, here 2 and 3, and the other part for the product is the sodium thing we done and okay. And the phosphate is 1, and here we are also have 1, and then I calculate the hydrogen 2 plus here the hydrogen 2 is 4, here is good, and I am good with this like number of the hydrogen in the product is equal number of the hydrogen in the reactant. And then I go to the check the oxygen is here 4 plus 2 is 6, and here 4, and also 2 uh, with the 2 multiplied by the oxygen is here 2 is 2 plus 4 is 6, and all these I figure out the balance of the formula is correctly, and then I start to make my calculation. First of all, I have to convert the sodium dihydrogen phosphate from the gram to the mole, plus also I have to convert the sodium hydroxide from the gram to the mole. Well, after when I convert this sodium dihydrogen phosphate, and I go to the periodic table, and 1 mole equal and the atomic mass for all these elements is 120. The gram cancel with the gram, and I end up with this number 0.0417 mole sodium dihydrogen phosphate. And then also I go to convert the sodium hydroxide from the gram to the mole. If you see 2.5 grams sodium hydroxide, 1 mole equal to 40 gram, and cancel the gram with the gram. I convert the sodium hydroxide to the mole, and then after that I make the mole fraction between sodium hydroxide and the sodium dihydrogen phosphate, and then I is like 1 to the 2, and after that I got like 0.03125 mole of sodium dihydrogen phosphate. And after when I got this the mole fraction result from this is the 2 reacting, I realized the sodium hydroxide it is the limited reaction because it has like 2 mole compared to this 1 mole of sodium dihydrogen phosphate. And then I take this the result from the sodium dihydrogen phosphate, and I make the mole fraction from the reacting this one with this one, the trisodium phosphate. If you see here, the result 0.3125 mole of the sodium dihydrogen phosphate and 1 mole of the trisodium phosphate equal 1 mole of the sodium dihydrogen phosphate, and they give me the same result because like the mole fraction between the reactant and the product is 1 to 1, and and after that, and I have multiply my result with what he give it to me, the molar mass. If you see the unit of the molar mass, it has gram over the mole, and my result here is the mole. I got the mole for the sodium, sorry, from trisodium phosphate. If you see this, the mole cancel with this the mole and just left the gram, and my end of the result for the trisodium phosphate is 5.112 gram. And why I do this the last step, because I want to cancel the sodium dihydrogen phosphate. I keep just like trisodium phosphate when I make the mole fraction between the reactant and the product. For this is stoichiochemistry, the other example, and he asks you like how many gram sodium dihydrogen phosphate are needed to react with the 28.74 milliliter of 0.225 molarity of sodium hydroxide. The molar mass for the sodium dihydrogen phosphate like 120 gram over the mole. And from this, the data or the number give me like from this example, if you see the sodium hydroxide, he give it to me by the milliliter and the molarity. My job here, I have to convert the sodium hydroxide from milliliter to the mole. I start with the converted like 28.74 milliliter, and the molarity, and if you remember the molarity mole over the letter, and the mole is like here, if you see this, like 0.225 mole over the one letter, and here, and we convert the letter to the 1000. The reason we convert it to the 1000 to cancel, and we match the unit between the sodium hydroxide and with the molarity. Here we change it. This the key concept of this one. Instead of to write one letter, we write like 1000 milliliter to match the unit, and then they cancel the unit and they keep just the mole for the sodium hydroxide. For this process, we convert the milliliter here, the milliliter to the mole for sodium hydroxide. After that, when we convert the sodium hydroxide to the mole, I make the mole fraction between sodium hydroxide and the sodium dihydrogen phosphate. If you see like 1 to the 2, and after that we cancel sodium hydroxide mole here, we cancel sodium hydroxide here mole, and just left sodium dihydrogen phosphate, and and with the mole, and like the final result 3.2 multiply 10 power minus 3 mole sodium dihydrogen phosphate. And after that, he give me already, if you see the molar mass of the sodium dihydrogen phosphate 120, but the unit gram over the mole. And after that, my final result here is with the mole, and he asked me about the gram, about the sodium dihydrogen phosphate, and just I multiply what he give it to me, and I cancel mole with the with the mole here and just left the gram. My final answer is 0.388 gram sodium dihydrogen phosphate, as when he asked me about this example. And this example also the stereochemistry but here in this time he asked me about the limited reaction or the limited reacting, and here the limited reacting, that means is in this part, is not in the not in this part in the product. We're looking for the reacting side. And here we start to read this example, like he says, like how many gram of the trisodium phosphate, here trisodium phosphate in the product can be produced when react 5 gram of sodium dihydrogen phosphate react with the 28.7 milliliter of the 2.25 mole of the sodium hydroxide. And also he gave it to me the molar mass, the sodium dihydrogen phosphate 120 gram over the mole, sodium hydroxide 40 gram over the mole, and trisodium phosphate 163.9 gram over the mole. And as I mentioned, first of all, I have to check the balance of the formula. And we sodium here 1 and here 2 is 3, here is 3, it's good. And phosphate 1 is good. And hydrogen 4 and hydrogen 4 here, and the oxygen like here is oxygen like 5, also here is not 5, sorry, oxygen is 6, 4 plus 2 6, here 4 plus 2 is 6. When I check all the element for the reactant and the product is like equal, and I make sure my formula is like balanced, and then I go to convert what he give it to me from the gram to the mole, and I start with the sodium dihydrogen phosphate, and from the periodic table I convert the 5 gram to the mole, and then I go to the sodium hydroxide. If you see the sodium hydroxide, he give it to me by the milliliter. As I mentioned on the previous slide, I have to match the unit about the molarity, and 28.7 milliliter multiply by the molarity 2.25 mole sodium hydroxide divided by 1000 milliliter. I cancel milliliter with this milliliter, and it's left just the mole of the sodium hydroxide. And then I make mole fraction between the sodium hydroxide with the sodium dihydrogen phosphate. If you see the mole fraction 1 to the 2, and I make the division, I get the final answer or my result. 0.129 mole is required to react with the sodium hydroxide, and the limited reaction is sodium hydroxide, because I do have the 2 mole for sodium hydroxide to react with the sodium dihydrogen phosphate. Therefore, therefore, the limited reaction is the sodium dihydrogen phosphate, and after that I know this the mole of the sodium dihydrogen phosphate, and if you see the unit is the mole, and I make the mole fraction between the sodium dihydrogen phosphate with the trisodium phosphate like 1 to 1, and after when I do the mole fraction I got the same number, and then after when I got the same the same number 0.0 417 here, and but if you see the unit in the mole, and I for the sodium, for trisodium phosphate, I multiply by this number. If I see the unit here, if you see the unit here, like gram over the mole, and the gram over mole, I cancel the unit, like mole go with this mole, I end up with just the gram, and my final result 6.83 gram sodium, trisodium phosphate, and this is what he asked me about in this for the balance reaction. If you see the balance reaction, it want to more focus on each element, and we want to make sure all the element in the reactant equal all the element in the other side in the product. For this, the displacement reaction, like sodium phosphate and magnesium dichloride, this the both reacting and react with each other and displace like element from each other, and they form like sodium chloride and the magnesium phosphate. The first of all, before I know all the balance number, I have to count the number of each element. For example, if you see here the sodium, like forgot number 2 and 3 and 6 for right moment. If you see the sodium here, the sodium, it has 3 sodium here in the reacting, but in the other side 1, and the chlorine is 2 chlorine from the reactant, but here is 1. I told myself which the common number and combine the chlorine and the sodium, and to make him equal is number 6. If I add the 6 here, and if I add 6 here and I add 2 here, and the sodium is become 6 here, and sodium also becomes 6 here, plus if I add the 3 in this magnesium chloride, and the sodium, the chlorine becomes 6 from this part, and equal to the product is chlorine is become 6 in this side. If I go back, I check like sodium 6, chlorine 6, and chlorine 6 is here, and sodium 6 here. I am done from the chlorine and the sodium. If I go to back of the phosphate, if you see the phosphate charge here, PO4 minus 3, that means if the phosphate when react with the magnesium, and the magnesium it positive charge because it has in the metal in the column 2 in the periodic table, and most of the time lost 2 electron from the shell, and this the 2 electron go down here, and the 3 from the phosphate and go down here like like a crossover, like X, like this one, like this one, like the 3 from the phosphate is go down here, and the 2 from the magnesium also is got down here. Like in reality, the minus 3 is here, and the positive 2 is here. And when you make the crossover, and magnesium is become 3 here, also the magnesium is here 3, and the phosphate is become 2 here, because I'm looking for subscript here. Subscript is 2, and also here this the 2 is 2 multiplied by the phosphate. I am done from the balance reaction, and without like add any additional number. And the balance reaction is required more focus, and be careful, and when you balance, and we have to add like a number, or sometimes we add like some fraction number and multiply this fraction number to get the whole number, and so on and so far. And like my final result, if you see my balance reaction, like 2, 3, 6, and we done from this one. And here is the additional information as I mentioned here. If you see here, when I say like -3, -3 is go to this down here in the magnesium, and the magnesium by the charge is +2, and they go here. And if you see this, the additional information for the how to balance between the magnesium and the phosphate, to get the final result, like the magnesium is 3 and the phosphate is 2. But the same thing, this like and as I discussed before, this one, like, just imagine like magnesium like this, magnesium +2, this is the shortcut, and phosphate BO 4 -3. And like a very shortcut, I do the crossover. I put the 3 here to the magnesium, and the +2 to the phosphate, +2. I end up with this, the final formula, like this one: magnesium 3 and phosphate is 2. And this like polyionic compound, I have to put them all this like between the two parentheses, like this one, two parentheses, like and my subscript is 2 just for the phosphate. The balance reaction take like more step, and be careful when you do the balance reaction, and we have to make sure each element in both sides, reactant and product, is equal. The other example for the balance reaction, how can to make the balance of equation. If you see here, the potassium iodide and the potassium in the column number 1 in the periodic table, and the iodide with the halogen also in like 7 column. And the lead nitrite, the lead is here. The charge of the lead is +2, but nitrite, the charge is -1. After, when they react, they give me the potassium nitrite and the lead iodide. If you see, just forgot right moment, this is the number 2 and number 1 and number 2 here. Let's start for the lead. The charge of the lead, the lead is +2. And if you see, the +2 is going in subscript here, and -1 for the nitrate is come here. But most of the time in chemistry, we not write the -1 or +1 in the subscript on under beneath any element. After that, if you see here, this the lead, also the same thing here. The lead is the +2, the +2 -1. Let's write it down. The lead here, the charge of the lead, +2, and iodide is -1. And when and the final form, if I write this one, the final form, like lead lead -1 and iodide 2, and the final form for this one be the lead and iodide sorry iodide uh, iodide I I is 2. Here if we look for this after when I make all this combine or displacement with the element for this reaction, if you see here this the iodide is 2, but iodide and the other side is 1. I have to add number 2 to make him equal. When I add number 2 to the iodide, I done from the iodide is 2 here, but I got the potassium is 2. I have to add the number 2 to the potassium to make him equal from the other side. And also I do have the nitrite is 2 here, it's equal to here, is good. And the lead is number 1 here, and the lead is number 1 is here. I am done for the chemical balance reaction. Chemical balance reaction, if you see this one, the sulfuric acid and react with the sodium hydroxide like acid and base, and the final my result is they give me salt, and with the H2O, the water. If you see here, and the number of the hydrogen on the other side is the number is 2, here, and the other one, and with the sodium hydroxide is 1 is the 3, and for the just forgot right now is 2 before I balance, and it says it's 2 is not equal. I have to make him like equal. I have to add like 2 here, and make him like 4 hydrogen, and 2 here is 2 hydrogen, and also I add 2 to make him like 2 hydrogen. 2 plus 2 is 4 hydrogen, and the hydrogen is 4. I am done from the hydrogen. I go back to the oxygen. The oxygen is 4 here, and 2 here is 6. And here is 2 oxygen and 4 oxygen with the sulfate is 6. I'm done from the oxygen, and the S is 1, is 1, and the sodium here is 2, and also here is 2 sodium. I am done from the balance reaction. Just I want to add some comment about this one, the sodium. If you check the sodium from the periodic table, the charge is positive 1. Sulfite SO4, the charge is -2. As I mentioned before, cross over this, and the final form like sodium is become 2, and sulfite SO4, like this the form. This the reason is mean the sodium is 2 here and sodium is 2 here, and we done from the balance reaction. After we check all the element from the reaction equal all the element in the product. And for this one, the oxidation number, how can to figure out the oxidation number? If you see the element are 0 or the free element, like let's say like silver or hydrogen or oxygen or fluorine by itself, and we equal to the 0. And we have to become familiar with the periodic table, and the periodic table, it has many groups, like 7 groups or 8 groups. from the first two group, and we call them like metal element. And the first group, and most of the air element is positive one, and second group from the element, most of the time the element they hold the charge positive two. The halogen is the seventh group in the periodic table. Most of the time is minus one, and the fluorine always is minus one. If the fluorine react with the oxygen more, and the fluorine is more electronegative than oxygen, therefore the oxygen is converted to the positive charge because the fluorine is highest electronegative compared to the oxygen. And also become familiar with the periodic table and the element and the oxidation number, and how to figure out to find the oxidation number. Let's start for this example. Like the silver, if this the free element is 0. Selenium tetrachloride, if you see the selenium from the periodic table, is most of the time it has positive charge. Like for if you don't know how can to figure out the oxidation number from this example, just imagine this is the chlorine from halogen. The chlorine is minus one, and the selenium is positive 4. As I mentioned, we cross over this number, and the oxidation number for the selenium is positive and 4, and the chlorine is minus 1. Or by other style, I say the selenium tetrachloride, this one tetrachloride, all over charge is 0. All over the charge 0. I say which number here for the selenium, like question mark. If I add it with the charge of the halogen chloride minus 1, multiply by the 4, it give me equal 0. The only number to make this the result 0 minus 4 is positive 4. Positive 4 plus minus 4, they give me equal 0 charge. And this is the other path to figure out the oxidation number for the element. But for the shortcut, if you can make a crossover, the crossover for the charge, you will figure out right away the oxidation number, and therefore the chlorine minus 1 and the selenium positive 4. Dinitrogen tetraoxide, here the same thing. If you use the one of this way I explained before, you will figure out the number of the oxygen minus 2, and the number of the nitrogen, the oxidation number is positive 4, and the trihydrogen phosphate, if you see this one, the hydrogen plus 1, oxygen minus 2, and the phosphor is positive 5. Just make this one like all over charge is equal 0, and hydrogen positive 1 multiply by 3 plus plus phosphor. I don't know how much the phosphor plus the oxygen. I know the oxygen most of the time carry out -2 multiplied by 4 equal 0. This 3 plus phosphor, I don't know, plus -2 multiplied by 4 -8. I told myself which number I can add it here to make all this all over charges 0, just positive 5. Positive 5, if I put like 3 plus 5, we become like positive 8, minus 8 is 0, and we figure out the oxidation number. Here the oxidation and reduction reaction, and we have to become like more familiar, and we have to know which one the lost electron we call like oxidation, and which element he gained like more electron we call like reduction. If you see here, and the iron is like oxidized because here the charge of the iron by itself here is 0 before, and the charge of this one is -2, but after when they react iron with the oxygen, the iron is the charges become +3, like he lost the 3 electron, and this one is become like oxidized. The iron is become like oxidized because he lost electron, and the oxygen from minus, and he get like reduced. If you see here like -2, -2 here, -2 and 4, and like 2 multiplied by -2 is -4, and if you go here and the other side is -2, just -2, he gain like 2 electron, and he become like reduce the oxygen. The same thing here for the sodium is 0, start with the 0, but here is start like +1, and here -1, and this one is become like loss of their oxygen, and this one oxidize, and the chlorine also is become reduced because here -2, because here the oxidation number of the chlorine -1 multiply by 2 -2 here -2. This the at the beginning of the reaction, but at the end of the reaction, the chlorine he gain 1 electron and become -1. And after that the copper is reduced to the 0. Here the charge of the copper is 0, and he gained like more electron before, because here the charge of the copper +2, and after the reactions becomes 0, and he become like reduced, and the chlorine, and here -2, and also he lost the one of the electron, and he converted from -2 to the -1. And all over for this slide, we have to figure out which they reduce and which they oxidize. How can I figure out this? Is the very basic for this one, very basic. If you see this, the both of these compound, or so both these of the element, iron, um, iron and the sodium, they start from the zero charge. They start from the zero charge here, zero charge, but they end up with not zero charge. This one oxidized, and the sodium also oxidized. And other side, vice versa, I make the decision for the oxygen is reduced and the copper is reduced, because if you see the copper here is also is a free element, is zero charge. He gained like two more electron and making like reduction. Thermochemical reaction, and this other topic for the chemistry and general chemistry 1045, and we have to calculate the energy. Most of the energy they measure by the kilojoule. For this the reaction for the phosphor react with the oxygen and give us like phosphate or the tetra tetra phosphor deca oxide, and it has the delta H, and this is the delta H. This is the sample of the enthalpy minus 3010 kilojoule. What mean minus? Like this, the reaction is very reactive and I call like exothermic reaction. And for the part A, he says if 90 grams of the oxygen react, how much heat is released. Here we have to convert the gram of the oxygen to the mole, and here the gram and what he give it to me multiply by the mole, and this is the number from the periodic table. We have the two oxygen and I got the mole of the oxygen, and then this is the number of the mole of the oxygen react with the one reaction. Here the reaction like one reaction and the mole fraction for one reaction over the 5 mole of the oxygen multiplied by the enthalpy. In reality, if you in reality we can write it down like this one, and like enthalpy, like here, like hold on, just give me 1 second. This one I can write it down like this. 3010 minus over the 5 divided over the 5, and the result is show up here. Because after they divide this one, and the other step from other part of this reaction, if you see here, this the amount is released when they burn like 5 mole of the oxygen. And the other part, or the part B, if the 6,500 kilojoule energy release, how much solid for the phosphate product is formed. Here, this is the energy for one reaction divided by this reaction by the enthalpy, and they give me they give me number of the mole, the number of the mole of the phosphate. Here, like, just imagine like this reaction, just like basic 6,500 divided by 30, 30110, and joule, kilojoule, 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 and kilojoule, kilojoule, and per mole, and this one cancel, and they give me this the number after when I make the division, and they give me the number like 2.6 2.6 mole. But he asked me how about the solid for the phosphate. The solid of this for the phosphate, the solid of the phosphate for this amount, or this the mole, just multiply, divide multiply, divide, and here the phosphate, I want to get rid of the mole, I have to put the mole in the bottom, mole, and like 1 mole, and I go to the periodic table, I count all the elements for this the compound, it equal like 283 point 88 gram, this gram, and this one cancel with this one after when I make the calculation. I multiply 2.16 with this number, I got the final answer is here. Final answer here, like the final answer. Hopefully you got this the question, and easy to solve, is not difficult. And for this one, the Hess law heat summation, most of the time we calculate the enthalpy by use the formula like sum all of the enthalpy of the formation product minus sum all of the enthalpy of the reacting, and all this the data is well given during the test. If you see this the reaction, dichrome tetraoxide, and react with the carbon monoxide, and they give me the chrome and carbon dioxide. And also they give me this the delta H formation for the dichrome tetraoxide. They give it to me this one, this the reacting, and the carbon monoxide they give it to me here, the delta H formation, and also the chrome they give it to me here in the product. But here it's soluble, is 0, and the carbon dioxide also they give it to me here. Just we add all these, but we be careful for the coefficient. I mean the coefficient when you add all this one is here 1, here is 3, and here is 2, and here is 3. If you see here the product, and the product of the chrome, like 2 multiplied by 0 plus 3 multiplied by the number of the carbon dioxide minus minus 3 carbon monoxide plus just 1 for the dichrom or tetraoxide, and you will find all the delta H of the reaction. And the major rule is this one: be careful, like product minus the reactant. And this slide they talk about the colorimetry. Colorimetry, like this, the closed system or the system assembly, and to measure the heat capacity for each element, and we can know we know the element, and we know the capacity, and we know the measurement of the how much heat they release. For this example, and he says when the 2.75 gram benzene, and this is the formula of the benzene, is burned in the excess oxygen in pump colorimeter. The temperature of the colorimeter rose from 26 to the 36, like the increase from 20 to the 30. The colorimeter heat capacity, he give it to you, this is the heat capacity, 11.7 kilojoule divided by Celsius. And he asks you about what the heat of the reaction per mole of the benzene. And he asks you about the heat of this reaction. First of all, we have to know the difference between the temperature. The final from the initial, we got the 10, and the 10, and also the delta T, or the final temperature, or the different the temperature between the final and the initial, and multiply by the heat capacity, we got this the number. Celsius, go with the Celsius, and this the heat is released, and kilojoule. But he asks you what the heat of the reaction per the mole of the benzene, and we go to convert the gram of the benzene to the mole. As I mentioned before, go to the periodic table. From the periodic table, and the molar mass, and we convert this the gram to the mole. And after when I convert it, and we divide it by this number, and we figure out how much the heat reaction per mole of the benzene. And this one, like 3268 kilojoule over the mole. And the other example here, if you see here, like 200 gram piece of the gold is heated to the 85 Celsius, and then quickly added to the insulated colorimeter, continue 175 gram of the water. The temperature of the beginning of the temperature 23.5 Celsius. The temperature of the water increase from 23 to the 25.6. Determine the capacity of heat of the gold. Assume no heat loss on the colorimeter, like in the closed system. If we see here, this most of the time we use this the heat mass and the specific heat and the delta T, and he gave it to me this diagram, and the specific heat we find it here, and because the specific heat is provided, and multiply by this one, and multiply by the like delta H, and we find the heat is like 1538, and here the specific heat for the here he asks you about here, determine the specific heat of the gold, assume the heat of the loss, and the specific heat this one, but all this one the heat capacity or for the gold, and it will be provided in the test, because all this the number they will give it to you in the test, like C, because this is the consonant number, and also just plug it with this the formula and the major formula, this one, mc delta T. For this slide, the assumption of the kinetic molecular theory. Gases are composed of the large number of the particles in the state of the constant random motive. The average of the kinetic energy of the gas particle depends only upon the Kelvin temperature. I mean, we use most of the time Kelvin temperature instead of the Celsius. These particles are much smaller than distance between the particles. Most of the volume of the gas is therefore empty space. The gas particles are considered the point having no volume. There is no force of attraction between the gas particle or between the particle and the walls of the container. The collision between the gas particle or the collision with the wall of the container are perfectly elastic, like bouncing. And none of the energy of the gas particle is lost when it's the collide with the other the particle or with the wall of the container. And here we transfer to other topic from the heat to the gas law. If you see this, the general mole of the constant or the formula become like this one, B like pressure 1, volume 1, pressure 2, volume 2, divided by temperature 1 and temperature 2. If you read this example, a sample of the gas has initial volume, like volume 1, the pressure 1, and 25 Celsius, like temperature 1. If the sample is composed to the volume of the volume 2, as the temperature increase to the temperature 2, what will be the new pressure? He asks you about the B2 after when, because the gas law, most of the time we deal with the Kelvin temperature. After when I convert the Celsius to the Kelvin, I plug all the number. If you see here, all the number, I am solving for the B2, and you will find the final answer for the B2, like 3. Here it's supposed to be like atmosphere, is not like air. Forgot this the air. This like honest mistake or the mistyping. Here like 3.18 atmosphere, and the final pressure. Just a crossover multiplication and solve for the B2, and you will find the final pressure. If they ask you about the volume 2 or volume 1 or temperature 1 or temperature 2, you do the same process all over again. The other slide, and they talk about the gas law, and he asks you about the density of the nitrogen gas at 25 Celsius, and they give you the atmosphere or the pressure and the torr. And be careful for the gas law, most of the time we use atmosphere, is not torr. We have to convert the torr to the atmosphere by use the formula, and like 1 atmosphere, and after when I find the atmosphere, and I have to use the other gas law. If you see this one, the gas law, BV and RT, and he asked me about the density of the nitrogen. The density of the nitrogen for this equation is like after when I convert the pressure to the atmosphere, I plug the pressure with the atmosphere, and I am looking to solve for the volume and the molar is like one of them, all of the nitrogen, and this the R is the consonant, and the temperature after when I convert it to the Kelvin, and I solve for the V. I find the volume 25.22 liter per mole of the nitrogen gas. I go to the periodic table and I find the nitrogen almost is 14 gram per mole, multiplied by 2 is 28 gram. I divide this one by this one. I got this the density. But if you want to convert, like if you want to convert the 25.22 liter to the milliliter, is okay, or you keep it like this one, is okay. But this one, the final answer is the density. This one for the nitrogen gas is the density of the nitrogen gas for this answer for this question. And we can solve for the density or the volume or the temperature or the molar mass for the compound to use the gas law. Here for the gas law, and as I mentioned before, and we can solve for the molar mass. We use the same thing, BV and RT. And if you see for this example, and they give me the sample unknown in the gram, and also the volume in the milliliter, and the temperature in Celsius, and the pressure with the toro, I convert it to the atmosphere. I convert the volume to the liter. I'm solving for the N, and I know the R is a consonant, and the temperature I converted to the Kelvin. After when I make all this the conversion correct, and then I solve for the N, I plug all this the number, I solve for the N, I got this the mole of this the compound, and he asked me what is the molar mass, and the molar mass of this the compound. And after that I divide this the gram and what you got from here, and I got this the molar mass equal like 77.58 gram over the mole. This like the mass of unknown sample. Of the partial pressure, like the total pressure, like partial pressure A plus partial pressure B, and plus partial pressure C, and so on, and the constant temperature and the volume. For this the formula, like the mole fraction is the fraction of the mole of the compound in the total mole of the gas mixture. And just keep in your mind the mole fraction of the gas A, the mole fraction, and the number of the mole of the gas divided by the total number of the mole of the with the other gas, and the partial pressure of the gas A, the partial pressure of the gas A, the mole fraction by the total pressure. Here the total pressure. Let's discover this example. A 5-liter flask container, 16 gram oxygen, 8 gram of the helium, at the temperature 25 Celsius, at the pressure 12.2 atmosphere. Here he asks you, what is the mole fraction? The mole fraction, this one, this the law of the oxygen in mixture, and what the oxygen partial pressure. The partial pressure, this the law. Let's start to convert the oxygen plus the helium to the mole. And after when I convert it to the mole, like the oxygen 0.5 and the helium is 2, I add them together, I got the total mole. I want to find the mole fraction. The mole fraction for the oxygen I divide like what I got 0.5 divided by the total of the mole, and I got 0.2. This is the mole fraction. He asked me about the partial pressure. This is the partial pressure of the gas A, and I multiply like 0.2 multiply by the total the total or the total pressure. If you see this, the total pressure here, it's 4.2 atmosphere. I got the partial pressure of the gas here, the partial pressure what for the oxygen, like zero, like mole fraction 0.2 multiplied by the total, I got 2.44 atmosphere. And just memorize this, the law and the mole fraction, mole of the individual of the gas divided by the total mole combined of these gas, and this become like mole fraction, and the partial pressure for the oxygen, and here multiply by mole fraction multiply by the total pressure from the question. Right, we use the gas law with the stoichiochemistry. If you read this, the example, what the volume of the hydrogen, they want the volume of this, the hydrogen. Gas collected over the water can be produced from the reaction 2.43 magnesium with the hydrochloric acid at this Celsius, 30 Celsius, and the pressure 750 torr pressure. The vapor pressure of the water of this the temperature is like 31 torr, and here and from the NRT, like BV NRT, this is the gas law. I have to use it to find the volume of the hydrogen. This one provided or is given by the question, and this is the constant is giving temperature. I know this is the temperature, and but be careful. I have to convert the torr to the atmosphere, and here I want to plug the number to find like the N here. So to volume for the hydrogen, but we have here the N. The N we have to figure out, and we use the stoichiochemistry to find the N. How I find it? Because he give it to me the magnesium 2.43 gram. I go to the periodic table, I convert it to the mole of the magnesium, and then the 0. After when I find the mole of the magnesium, I want to make the mole fraction between the magnesium and the hydrogen is 1:1, and I got the same number, and after that I solve for the volume, and for the volume of the hydrogen I plug all my number again, and after when I convert like the Celsius to the Kelvin, and then like 30th Celsius to the Kelvin, and after when I plug all this the number, I solve for the V, and I will find my final answer, the volume 2.63 liter. In this slide, we transition to the different idea. We become like a quantum chemistry, and the quantum chemistry is like a huge topic and more complicated process. And for this table, and just beware when I discuss this one. Maybe you will face it like every single day if you go like advanced chemistry. Here, like N is the number of the energy level, like 1, 2, 3, 4, and up to the 7. And here the possible value of the L. I mean, let's discuss this one like subshell, the subshell first. The s orbital, it has one orbital. This is the dash line, just one orbital, and the p orbital, it has three orbital, like three dash, and d orbital, it has like five. 1, 2, 3, 4, 5 orbital, and f orbital, it has like 7. 1, 2, 3, 4, 5, 6, 7 orbital. If you see here, like the L, the L value for the s orbital most of the time is 0. The L. And the L for the b orbital most of the time, the L orbital for the b is 1. And the d orbital L is 2. And the f orbital L is 3. If you see this f orbital is the 3. And each orbital, like this, the single orbital occupied by 2 electrons. This one like 1, 2, 3, 4, 5, and 6. And the same thing for the d and the f orbital. Here, like here, like 2 electrons, 6 electron, 10 electron. Here, the 14 electron, and so on. And the value of the ML, and this one, the s orbital, most of the time ML is equal 0, and the B is like, it's like 1, 0, minus 1. That means like 1, 0, minus 1, or like this, or by other word, like the b orbital, as I discussed, the L is equal 1. But if I want to figure out ML, I have to subtract like with the same number, like 1. I say like 1 minus 1 is become 0. This is the first, and the 0, and 0 minus 1 is equal minus 1. And if I want to write all over again the ML, I say 1, comma 0, comma minus 1, and use the same idea for all other D and F orbital to figure ML. And this, if you see here, the value, if you see here the value of the S is like the value of ML is 0, B the value 1, 0, minus 1, and the D value, if you see this, the 2, that means, let me to help you to understand this one. How can I figure the 2 value? The 2 for the D. This one, if you see this, the D value is 2 for the L, but if for the L is equal L, for the D is the 2. If I want to figure out ML for this, what I have to do, like 2 minus minus like in each term minus 1, and after that what I got the result from here like 1 minus 1, and what I got result here like 0 minus 1, and what I got result from here like minus 1, also minus 1. I'm stopped when I reach like minus 2, and if I got the result here like 2, I start with because the value of the L is 2, comma 1 minus 2 is 1, and comma minus 1, 1 minus 1 is 0, comma, and after that 0 minus 1 minus 1, and comma minus 1, and also minus 1 minus 2, comma. If you see ML, how many value 1, 2, 3, 4, 5 is exactly the number of this the orbital, because the D orbital it has 5 orbital, 1, 2, 3, 4, and 5, and so on for the F orbital. Use and how can to figure ML value, and just like in each time just subtract by the 1 to find the number of the ML value. This one, this the value, and the number of the orbital, as I mentioned. If you see here, the S is like 1 orbital, and the number of the orbital in the subshell. Sorry, here, just look for this. Is not look for this this diagram. The S is 1 orbital, B 3 orbital, and D 5 orbital, and F 7 orbital, and each orbital occupied by 2 electrons. And the total number of the electron, sorry, the total number of the subshell is 16, and this one here also here, and the total number of the orbital in the shell, this one, but and this one. After when I discuss the NS, L, ML, and the orbital, and D, and the S orbital, and B orbital, if you go to this the periodic table, and if you see this the column A and column B, most of these orbital is end up with the S orbital. That means like outer shell or the latest orbital is end up with the S, like column 1 and column 2. And the transition metal, if you see the transition metal, most of all of them, they end up with the D orbital. D orbital. Don't worry about the number here, just focus about the D orbital. And the other one, non-metal, they end up with the B orbital, and metalloid, or most of them, they end up with the F orbital. And if you see, as I discussed before, and the S orbital, it has 1 orbital. B orbital, it has 3 orbital. And the D orbital, it has 5 orbital, 1, 2, 3, 4, 5. And F orbital, it has the 7 orbital, 1, 2, 3, 4, 5, 6, 7 orbital, and each orbital occupied by 2 electrons. If you see like here 1 and 2, 1 and 2, 1 and 2, and also for rest of this orbital. And be careful and remember the periodic table and the first two column metal, s orbital, transition metal, d orbital, non-metal, b orbital, metallite, and f orbital. Keep it like very simple and basic, and I will discuss this one later. Next slide. For the electron configuration and how can we figure out the electron configuration, and we have to understand the orbital as I discussed in the previous slide. The lowest energy for the orbital is S, like s orbital, and this is the lowest energy, and they come b orbital, the highest energy, and they become the other one, d orbital. D orbital is second level high energy, and the farthest one is the f orbital and become highest energy. Why the highest energy? Because if you remember this, the proton and neutron, and this the positive charge of the nucleus, and they surrounded by the orbital, and this the s orbital is very close to the core of the atom, and this become like zero energy. The electron they not required to put more energy to keep it surrounding around this the orbital. But compare with this, let's say f orbital, the f orbital, imagine the electron is too far from the radius from the nucleus, from let's say f orbital. This f orbital is too far from the nucleus, and they require more energy from the electron to keep it in the same orbital and interact with the nucleus. Therefore, the f orbital is the highest level energy to keep the electron run or circle around the nucleus. Therefore, therefore, the f orbital is the highest energy, and the s orbital is the lowest energy. But for the electron configuration, let's say the neon. The neon it has the neon here. The neon it has the 10 electron. 10 electron. I start with the first 1s orbital. It has 2 electron, 1 and 2 electron. Minus 10 is left 8. And the second level for the highest level energy is 2s orbital. 2s orbital also it has 1 orbital, and take the 2 electron, and the total is 4. This is the 4 electron minus 10 is become 6 electron left. 6 electron. The second level highest energy is the 2b orbital. 2b orbital, which is like has a 3 orbital, and when we line the electron configuration, and we have to follow the style of the rule, and we have to line on the left here 6 electron. After subtract like this one, 1, 2, 3, 4 from the 10 is left 6 electron from the 10. I start to line the electron like this direction, 1, 2, and 3, and then I come back again to the first orbital. I say like 1, 2, and this is 3, and the total of the electron occupied this orbital is 6 electron. I am done from electron configuration. Please go to your textbook and see how the electron configuration, how can to use the energy level from starting from 1s to the, let's say, 6x or 5s, but between 1s and the 6 or 5s we have the b and d and f, and we have and go back and learn how to write down the electron configuration, and all this the detail you will find it in the textbook. In the textbook, and for how can to write the electron configuration. And this one, the periodic trend summary, and just be aware about the atomic size. As the atomic size, if we go down here, they increase. Okay, that means if we go like from the up to the down, and the ionization energy and the electron affinity is decreased. That meaning there's the atomic size, like if I go from top to the bottom. And the other, the effective nuclear charge, like effective nuclear charge, and if you go down is more shield, and it also decrease if you go down, because more electron and more electron shield, and this the effective nuclear charge, like nuclear charge has become like less. And how can I calculate this one? The actual nuclear charge minus the shield, and you will find the Z effect nuclear charge. If you go down, also there's the more shield and more shielded, and will be decrease. And just remember, if we go up, and this one is become an increase. And atomic size, this that meaning if you go down and increase, if we increase the atomic size and decrease the ionization energy and decrease it with the electron affinity. But if you go up and strong attraction, and they both the term like ionization energy and electron affinity will be decreased, like if we go like from bottom of the periodic table to the top of the periodic table. For this slide, we have to like draw the Lewis structure or Lewis dot, and the major or the backbone of the Lewis structure. This is the octet rule. What does mean the octet rule? The octet rule, like each element in the periodic table, each element for the say the carbon, and surrounded by 8 electron around this the carbon, and we call this one octet rule. And but we have some exception, and the exception like for the phosphate or silver or something, and we don't have like octet rule, and we not follow the octet rule. For the example, let's say how can I make the Lewis structure or Lewis dot? Let's say for the methane, CH4, and the first of all I have to calculate the valence electron. The valence electron for the hydrogen is 1, equal 1. But I do have 4, 1 multiplied by 4 is equal 4. And the valence electron of the carbon is equal how much carbon? The valence electron is 4. Is 4. And if you don't know how the valence electron, we have to go to the electron configuration, and you will figure out the valence electron for the carbon. For example, the carbon from the periodic table, the carbon, and it has like 6 electron, and as I mentioned, for the electron configuration, we can write the electron, and they start with the 1s. For this, the carbon S1, it has one orbital, but it's occupied by 2 electrons. There's the 6 electron minus 2, left is 4, and the second orbital is 2s orbital is also occupied by 2 electrons, and and 4 minus 6 is 2 electron, and the second level energy is 2b orbital. 2b orbital has 3 orbital, and occupied by 2 electron. This is the 2 electron. The valence electron, we not consider the ground state energy like 1s. The valence electron supposed to be like this. Like this one, this is the orbital, and they hybridize the s and the b, and 1, 2, 3, 4 orbital, and this is the sorry, 4 electron, and this is the electron or the valence electron for the carbon. After that, I want to solve for the Lewis structure. I have to line up the carbon surrounded by the 8 carbon, by 8 electron, sorry, by 8 electron. Therefore, I want to see this. I place the carbon in the middle, and I do have how much electron, valence electron. The total is 8 electron, and each hyphen like this one is represent like 2 electron, like electron here and electron here. But in most of the time, we write like the dash like this, and like this, and like this. And each dash it has 2 electron, like 1, 2, 1, 2, 1, 2, 1, 2 electron. Therefore, we use like a dash line to represent the 2 electron. And we have the 8 electron here. I have to replace 8 electron around the center atom, like this 1, so 2, 4, 6, and here 8. And after that, I place the hydrogen around the methane, and this one, and this hydrogen, because we have the 4 hydrogen. And this is the Lewis structure for the methane, which is the CH4, and we come like and we transfer this one, the molecular formula, to the Lewis structure, or the form of the Lewis structure that for the methane. And the molecular the formula charge, let's say for the same element, methane CH4, if I want to find the formula charge, and I can do like this one, I use this the formula charge. The number here, as I mentioned here, the CH4, I want to find the formula charge for formula charge. I have to know like the valence and number of the valence of the electron, as I mentioned, is 8 minus lone pair. I don't see any lone pair here, is 0 minus sorry, here I have to say this to start all over again. I don't want to confuse you. Here this the CH1, 2, 3, 4 hydrogen. this is the hydrogen, this is the hydrogen, this is the hydrogen, and this is the hydrogen, and this equal the CH4. And the number of the valence of the electron, let's say for the carbon, is 4, and minus the lone pair. I don't see any lone pair here. Is 0 minus the number of the bond, which is the same 1/2 electron bond. Yeah, I remember I told you each line is represented by 2 electron. I got here 8 electron minus like 8 divided by 2, and this one take away and become 4, and we end up like 4 minus 4 equal 0. And the formula charge for the carbon is like here is 0. And just keep it very simple and just follow the law for the formula charge to find the charge in each element, like for the carbon or the hydrogen or the oxygen or any element in the compound, and so on. And just be careful when you apply this one. The valence of the electron for by itself the compound for the element, and the lone pair if you find it, and minus the number of the bond or the number of the electron divided by 2, and you will find the formula charge or the charge of the specific element in that compound. This slide he discussed like the valence shell electron pair repulsion theory for the geometric and for the molecule. And if you see this one, linear, triangle, planar, tetrahedral, and triangle bipyramidal or octahedral. But here we have to know like the hybridization. And if you see this, just the hyphen here is we call them like sigma bond, and the bond is like double bond, represented by like this, like carbon, like it has 2 carbon, and this one we call like sigma bond, just like 1 bond. But if the carbon is touched by double bond, and we call this one by bond, and also sometimes the carbon is touched by 3 bond, also we call this one 2 by bond, like this one and this one with 2 by bond. And the sigma bond is more strong compared to the bi bond, and the sigma bond is like bond end to the end, but I mean the bond end to the end has become like the overlap of the electron is more strong than by bond, which is like side by side, or here the side by side overlap for the electron. And how I know the hybridization, if you see like linear, we say like sp hybridize, like sp hybridize like this, like carbon has 3 bond, hydrogen acetylene, and on this like 180 degree, and we come like sp hybridize. But if we break this bond and make him like carbon and hydrogen, 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 and the hydrogen, and the hydrogen will come like this one, sp2, sp2 hybridize, sp2 hybridize, and they not give me the linear. Sometimes they give me bent, or like the bent, what's that mean? Triangular planar, the shape triangle planar or triangular planar, like or the bent, like sometimes like H2O, H2O, this is the water, also become like bent, bent, and from the linear bent, and sp2, sp2, sp2 hybridized, because this is the two lone pair, they push down, there's the bond, and they not make them in linear form and become like the bent, and they take the sp2 hybridize, and the other one and sp3 hybridize, the sp3 hybridize, and like the methane I discussed it for the previous slide. If you see the methane, it has like 4 hydrogen bond. If you see here 4 hydrogen bond, we call, if you see this, the 4 hydrogen, like 1, 2, 3, 4. Just focus here. 1, 2, 3, 4. The 4 hydrogen bond around the center atom, and we call this one Sb3 hybridized and tetrahedral or triangle bipyramidal. And the sp3d hybridized is very hard to drawing. Just focus about like how many bond, 1, 2, 3, 4, 5, and octahedral, and with the sp3 D2 hybridized, and also 6, 1, 2, 3, 4, 5, 6 hybridized, and this one become like sp2 hybridized. And keep it very simple, like linear, like this compound sp, 3 bound sp2, 4 bound sp3, and 5 bound sp3d, 6 bound sp3d2, and for this hybridize and the electron between the orbital.